Welcome, everyone. It's with great pleasure that I introduce Klaudia Protušová today. She's going to be visiting for the next 5.5 weeks now. Hi, Brian. Klaudia is visiting from the University of Heidelberg in Germany, where she's pursuing her PhD that is about to be done in the next few months. So instead of working on her thesis, she decided to come to Hawaii to visit us. So we should be all happy for that. Klaudia is an expert on everything in the epoch organization, studying galaxies, what galaxies do, how galaxies behave in the epoch organization, if they look double, if they look single. Oh, spoiler. She's now in the office of Nick, that is 316, or I don't remember. Anyway, Nick's office. And she will be here. And today she will introduce her work, that is Proximate Galaxy near high-redshift QSO, as window into the epoch organization. So, stage is yours.
Yes. Thank you so much. Hi, everyone. It's really a pleasure to be here. Also, this is the first colloquium I've ever given, so if it's too short or too long, or I just go off the rails, I'm really sorry. Hopefully it will be fine. And if you saw the listing of this talk, you might have seen me holding my cat. And I just want to say, oh, it's not working. Okay, so this is my cat. His name is Charlie. And as you can see, he's highly educated. He can read actually even magazines and so on. So he helped a lot during my study, so I just wanted to include him. But let's get back to the talk itself. So let's start with the history of the universe. Let's take a small stroll before I introduce what epoch of reionization is. So let's start at the very beginning, the Big Bang. The Big Bang has been introduced as a theory in the early 20th century when Lemaitre and also Friedman saw that the universe is expanding. This was then also confirmed with Hubble's observations of expanding universe. And when we run the expansion backwards, we find out that the universe must have started in a very hot, dense, and very small point at the beginning, which was then in the 50s, kind of ironically, but also apparently not, as I read today, was named the Big Bang theory. After that, we enter the inflation era, where the size of the universe changes by a factor of 30, somewhere I saw 60 as well, where you go from the size of about 10 to the minus 30 meters up to about 10 centimeters, which is a huge change when you think about it. And the inflation theory has been introduced to solve a few problems. First one was the flatness problem, where when we look at the universe itself, it seems very flat, no matter how far into the history of the universe you go. And the inflation actually solves this problem. Another one is the horizon problem, which shows us that when you look at two parts of the cosmic microwave background that should never have been in contact with each other, they're actually in thermal equilibrium. So they must have been close at some point. And last thing that it solves is the magnetic monopole problem, where according to the GUT theory, I hope it's pronounced as GUT, maybe it's GUT. I don't know, I'm not an expert in that. It says that we should be able to observe magnetic monopoles, but we don't see them anywhere, while the inflation kind of solves this problem by keeping them away from us. Another part in the history of the universe is the creation of the cosmic microwave background. So in between the inflation era and the creation of cosmic microwave background, all the particles of baryonic matter were created. There was this hot soup of plasma, protons, electrons, photons flying around everywhere. And the universe was too hot for any of the photons to escape or for the electrons to actually bind to the protons. But as we go further into the history of the universe, it starts cooling down enough for the electrons to bind back into the protons, and therefore the photons are able to stop being scattered across free electrons, and they escape into the universe itself. And this gives us the first picture of the universe. Some people call it a baby picture of the universe. It's when the universe was about 400,000 years old, and it also marks this time when the universe starts being filled with neutral hydrogen. Then we move to the dark ages, which I filled out with just black part because I don't know what else to put in there. I think this is quite representative. all the CMB photons that were created at the recombination era, they at the time were corresponding to the black body temperature of about 3000 Kelvin, which puts them in the red part of the visible spectrum. And as the universe expands, all of these photons are quickly redshifted outside of the visible range, and therefore the universe is plunged into darkness. There are no other sources of any visible or higher energy photons. All that is present in the universe is primordial gas, which consists of neutral hydrogen, neutral helium, and traces of other elements, mostly lithium, and I don't know if I'm going to pronounce this correctly, deuterium? Yes, perfect. Good enough, exactly. And all of these, they can emit photons, but they are in the radio frequency. So if you somehow manage to travel back into the dark ages, you would not be able to see anything. And then we move on to the first light, when the first stars and first galaxies are being created. Now, these stars that were created at first, also marked as population-free stars, they were created from the primordial gas. So almost no metals present in these stars, and therefore the gas that formed them couldn't have fragmented as much because the cooling wasn't as efficient as in the gas that we see today. And therefore, some theories show that these primordial stars had really high stellar masses of about 300, sometimes I saw 1000 solar masses as well. And this makes them very hot and also very bright, but also incredibly short-lived. So they probably turned on, shone for a few 100,000 years to a million years, and then blew up and started enriching the entire environment of the universe. They are also the first sources of ionizing radiation. So as we know, the universe at the recombination era was filled with neutral hydrogen, and now there are first sources that are actually ionizing this hydrogen back into its ionized state. Also, it was thought that JWST would be able to find these population-free stars. So far, no luck. I also am not very optimistic that we'll ever be able to see them, because it feels like the start when the first stars emerged is being pushed further and further into the history of the universe. So I don't think we'll ever be able to find it. But one cool thing is that we actually see galaxies very early in the universe at about 280, that's the word I was missing, million years after the Big Bang, which puts it at redshift about 14.4. So that's the current record holder. I haven't heard if there's a further one, so hopefully my information is still up to date. And from the first stars, we actually move to the epoch of reionization, which marks the second phase transition in the history of the universe. So the first phase transition was the recombination era, when the CMB was created, when all the electrons bound to the protons and created neutral hydrogen. And this one is actually when the first sources of ionization are ripping these electrons from the protons and creating ionized hydrogen, which is filling the entire universe until today. Now let's take a slightly closer look. That took a while to load, and that's because all of these galaxies are like a separate object, so my laptop is struggling a little bit. But it is thought that the epoch of reionization started at about redshift of 30, which corresponds to about 100 million years after the Big Bang. But as I said, the time seems to be pushed further and further, so who knows, maybe there will be a new reionization model. And each source of radiation, so stars, galaxies, quasars, etc., create bubbles of their own ionized gas around themselves. As the history progresses, all of the neighboring bubbles start connecting and connecting and connecting until you end up with the reionization being finished at about redshift 5.3, which corresponds to 1.1 billion years after the Big Bang. And we are still in the ionized state until today. Now, if we take a closer look at what's happening, in reionization era, there are two forces fighting against each other. First one is the recombination rate, or how quickly the ionized hydrogen can recombine back into its neutral state. It depends on the clumping factor of the intergalactic medium. It depends on how much neutral how much ionized hydrogen there is, so how many protons and electrons you have, etc. And then there are the light force, I would say. This is the dark force, this can be the light force, fighting on the other side, which is the ionizing output of sources, which is reionizing the universe. Now, I drew a galaxy here, but it can be quasars, it can be stars, any other source of ionizing radiation you can think of. What's important to note is that these ionizing photons have energy higher than 13.6 electron volts, which corresponds to a wavelength shorter than 912 angstrom. So if we take a closer look at this light force, we can describe it by two physical properties. The first one is Xi-ion, or called ionizing photon production efficiency, which tells us how many ionizing photons are produced by galaxies, quasars, etc. Another force, another physical property is how many of these ionizing photons, which are produced in the galaxies, are able to traverse through the interstellar medium of these galaxies and escape into the intergalactic medium. If we have galaxies that are very rich in neutral hydrogen, they will block the escape of the ionizing photons into the intergalactic medium. So you can be producing a lot of them, but if nothing is escaping, you're not really reionizing the intergalactic medium. So these two forces are very important. Now, even though there is a lot of questions still remaining about this epoch, one of the ones that I was dealing with a lot is what are the main key drivers behind epoch of reionization, or what kind of object produced the most amount of ionizing photons in the epoch of reionization. Now, the way to calculate this, and I'm sorry about my crudely drawn UV luminosity function, I tried my best, hopefully it's legible. So what you do is you take your source, for example, a galaxy, and you figure out what its ionizing output is on a global scale or a population scale. So you have F escape and Xi-ion. Then you calculate how many sources you have in a unit of volume per some UV luminosity. You calculate how many sources you have. You figure out what the ionizing output of these objects are, and you can compare it to your simulations and compare it to when the epoch of reionization ended. And you're like, okay, galaxies are giving me most of the photons I need. Therefore, galaxies are the main output of, main drivers of EOR. It is actually thought to be galaxies, but mostly the faint ones and intermediate ones, because there's a lot of them. There's way more of them than of the bright galaxies. And therefore, it's community accepted mostly that these are the main sources. But it feels like every single year there's a new paper that's like, actually, it's quasars, or actually, it's not galaxies, or oh no, now we have too many photons. So it's still very questionable. But this is what you'll see in textbooks and in a lot of talks. But what's important is that even though we can calculate how many galaxies we have, and it's not super hard getting the ionizing photon production efficiency of these sources, what's very hard to measure is the ionizing fraction of escaping radiation from these galaxies. And that's because even though the ionizing radiation escapes the galaxy itself, as soon as it gets into the neutral IgM, it starts interacting with the IgM, it's scattered, and we cannot see it. So even though it's escaping, we don't know what it is. And that's quite a huge problem in calculating the ionizing budget of the EOR. Why is this? Oh, just a little video to show why this happens is here, this is a spectrum of a quasar, and you can see the light traversing. Can you see my? Oh, okay. And you can see the light traversing through patches of neutral hydrogen. And what you'll see is interactions of the Lyman alpha transition, then the Lyman beta transition. And then here somewhere is where the Lyman continuum starts. So all the ionizing photons which get immediately suppressed. So let me play the video. So yeah, we start with nothing, but as soon as we hit neutral hydrogen, it starts interacting, so Lyman beta, and now we had a huge suppression in the ionizing part of the spectrum. And if you go through enough of neutral hydrogen, all of this gets absolutely suppressed. So we basically end up with Lyman alpha and then nothing, if you go deep enough into the epoch of reionization. Okay, I think I need to click. Oh, yes. Okay, so if we cannot do the ionizing observation directly, what can we do? We can maybe turn to indirect tracers of ionizing escape. And one of these was proposed to be Lyman alpha. And that's because Lyman alpha, as you saw in the previous video, also reacts with neutral hydrogen, or reacts when there's neutral hydrogen present. So let's say in a galaxy we have stars and they emit Lyman alpha radiation, but also ionizing radiation. It hits neutral hydrogen in the interstellar medium, and then some of it escapes outside. Now, if we take a closer look at what's happening, the Lyman alpha takes the electron which is in a ground state and puts it in the first excited state. So it goes up and it's immediately re-emitted back, but it scatters in space, but also a little bit in frequency. So you get a kick either in the blue part of the spectrum or the red part of the spectrum. Now, why is this important? Is because when we look at the cross-section of Lyman alpha, you can see that when you are exactly at the wavelength of Lyman alpha, your probability of interacting with neutral hydrogen is sky high, basically 100%. But if you go a little bit in either red or blue part of the spectrum, it starts dropping quite drastically. So you get a little bit shifted to the blue, you're fine. You will not hit the 1 to 2nd transmission line. If you go a little redder, you don't have enough energy to even excite it to the first state. So basically, you are starting to create escape channels in the both red and blue wing of the line. If you do Lyman alpha radiation modeling, you can actually see that it creates some funky shapes. So these are the escape channels that I was talking about. And the more neutral hydrogen you have that the Lyman alpha photon has to go through, the more it needs to shift in order to be out of resonance with the neutral hydrogen. So the more you have, the more neutral hydrogen there is, the further away the peaks are separated. And then some people had a thought that's like, okay, so if the double peak profile of Lyman alpha, which you can see here, traces how much neutral hydrogen there is in a galaxy, and this neutral hydrogen also stops the escape of ionizing photons out of these galaxies. Can we maybe link them together? And this was tried at low redshift galaxies at about redshift 0.3, so basically local universe. I know it's not, but basically. And it has actually been found that in these galaxies, you can actually see the ionizing radiation. So they measured what the escape fraction was, and they also measured the separation of the Lyman alpha line. And they did actually find that the closer the peak separation is, the more ionizing radiation is escaping from these galaxies. And the further away they are, the almost nothing is escaping. So people are like, okay, so now we have a tracer we can use maybe at high redshift. That will be cool. But what's important to note is that at low redshift, about half to 1/3 of all Lyman alpha emitters, so galaxies that have Lyman alpha line, showcase this double peaked Lyman alpha line profile. But at high redshift, you could count them on your hands, maybe if you borrowed your friend's hand, if you're feeling optimistic. So not a lot of sources. And another part that's very important to know is that can we actually see a completely unattenuated blue peak? Now, what I mean by that is that, let's say we have a galaxy in an ionized bubble, then we have galaxy in an optically thick ionized bubble, and then in the neutral IgM. The IgM, when it's neutral, completely suppresses it because you escape the galaxy and you're immediately scattered on neutral hydrogen. But if you are in a bubble, you have some time to redshift the blue peak outside of resonance with this neutral hydrogen. But even if you are quite deep in a bubble that's created by a galaxy itself, you don't have enough time or enough space to redshift completely the entire double peak profile. And therefore, you're not seeing the complete equivalent width or flux of the Lyman alpha line. And also it moves the peak that you see here. So it seems like the peak separation is lower than it actually is. Okay, so I introduced a tracer that might be good, but it seems like it's not actually good. But I have one solution, and that's if we look into proximity zones of quasars. So the good thing about proximity zones of quasars is that they are much bigger than any ionized region or bubble done by a galaxy. So it can extend up to 5, I even saw 10 proper megaparsecs. What it means is that the quasar itself is emitting its ionizing radiation. It reionizes a part of a region, and that gives us some flux blueward of the Lyman alpha line that is able to be transmitted all the way to us. So, oh yeah, and what's also important to note is that the longer the quasar is on, the bigger the proximity zone gets. So here we have a comparison of a young quasar and an old quasar. So in the young quasar, the proximity zone is teeny tiny, but in an older quasar, it extends quite far. So you can have more time to redshift any blue peaks outside of resonance with the neutral hydrogen that's in this part. Okay, so let's say we have two double peaked Lyman alpha emitters. We plop one into typical IGM at redshift 5. What we would see is a redshifted right peak of the Lyman alpha line. We would have no chance of seeing the blue peak. It would be completely gone. But if we plop this galaxy quite close or close enough to the quasar, the quasar ionized region is big enough for the blue peak to be completely redshifted out of the resonance with the neutral IGM that's in this part. And therefore, we could be able to actually see the fully unattenuated blue peak of the double Lyman alpha line. Okay, so I said that double peaks at high redshift are already pretty rare. So any guess on how many proximate double peak LAs do we have? Yes, exactly. It's 2. So the first one was described. Oh, yeah, sorry. What I forgot to say, maybe I said it, I forgot, is that we see the real peak separation equivalent width of the line. But yes, as Emma said, there are 2. So the first one was described in 2020 by my supervisor, and it was found at redshift 5.8, and it's a fairly bright guy with an absolute magnitude of -21. And when we look at the Lyman alpha line of this galaxy, we can see it's very wide. If we run the relation that I showed you before, we see that less than 1% is escaping from this galaxy. So if we take this as like the population-wide escaping from galaxies that are of this magnitude, we're not doing that well. Maybe we would not have enough photons, because usually models assume that the galaxies are emitting about 10% into the IGM. But all hope is not lost to use this tracer to find leakers. And that's because in 2024, Vega 1 did a short letter about a new protocluster found around quasar J0910-0414 at redshift 6.6. And he posted this figure, which shows the high resolution spectra of the Lyman alpha lines of all the galaxies connected to the protocluster. And we see here that this is in the 2D spectrum, it's much more visible than in the 1D, that there are 2 blobs here. So, we got excited. We're like, oh no, it's probably another double peak. And then when I looked at the data myself, re-reduced the spectrum myself, we saw that yes, indeed, there are 2 peaks in the Lyman alpha line. You can see them here. It looks much closer than what was before. The peak separation seems smaller. So this could be a good candidate to be a leaker of ionizing radiation. And that's what we set out to do in my first project. And we were very lucky with the number of data we have about this galaxy. So first of all, I realized actually when making these plots that a lot of the data were observed here in Hawaii. So you have the Subaru data, which was used to actually photometrically Is Subaru here?
Yes, but there is no Gemini.
I know. There some of these actually some of these have been on Gemini, but I didn't have access to the data. I only had access to the KEGG data, unfortunately.
Yeah.
I think so. Or maybe I'm thinking of another thing. No, that was Magellan. Sorry, that one I don't have access to. But I'm pretty sure some of these are actually from Gemini. But yes, so, oh, let me go back. So yes, we have Subaru data, which was used to select photometrically for Lyman alpha emitters. So first it was used as a dropout, and then there was a narrowband to actually find the Lyman alpha emission. Then we have the high resolution spectra of the Lyman alpha line from KEGG that I showed you before. Then we have JWST photometry in the 115 filter and also HST photometry in the 125 filter. And then, as basically a miracle, this quasar, around which the galaxy is situated in, was part of the ASPIRE survey, which focused on imaging 25 high redshift quasars, focusing on the rest frame optical part of the spectrum. So they took more photometry with JWST, and there was archival HST photometry as well. But they also made slitless spectra in the 356 filter of all surrounding galaxies and quasars, etc., in high resolution, which was focusing on the O3 doublet and the H beta line of the galaxies. So they were targeting O3 emitters. We were lucky that this galaxy is both a Lyman alpha emitter and O3 emitter. So all in all, it looks like this. Oh, God, I forgot one thing. We also have low resolution near-spec MSA spectrum in PRISM. Okay, but let me go back. So all in all, it looks like this. We were very lucky that near-spec is so sensitive because it actually managed to also image the UV continuum of this galaxy. And then we see the Lyman alpha line. We see some conglomerate of H gamma, O2 and O3, but it's we didn't really deal with it because it was too low flux and too many lines merged together. Then we have very nicely imaged H beta, the O3 doublet, and then the H alpha line. Then we of course have the high resolution Lyman alpha spectrum, and then the high resolution O3 spectrum. What you can see here is the H beta is missing, and this is because unfortunately there's a bright source near the galaxy itself. So in the WFSS extraction, it was over subtracted and we lost the high resolution H beta imaging, but we at least have the low resolution one. Okay, so we have all of this. Now with the data, we could assess the global properties of this galaxy itself. When we looked at the spectrum itself, we measured the UV magnitude of this source. We saw that it's lower than the previous one. So we are moving into assessing the ionizing properties of galaxies that are fainter than the previous one. But look at the UV slope. It's super blue. It's very, very steep, which kind of points it away from a typical like population model of galaxies at this redshift. So it's quite an extreme galaxy. It's also low mass, so it's 10 to the power of 8-ish solar masses. It's dust poor and also metal poor. When we compare it to low redshift sources, it actually falls in the category of extreme emission line galaxies. So these are from redshift 2 to 3. And as you can see, the equivalent width of O3 and H beta is quite high. It's on the higher end. And also this is the redshift of the Lyman alpha peak, so where the red peak is. So it's also in the lower part. But the equivalent width of the Lyman alpha line is the highest out of the entire sample. So I would say that it is an extreme emission line galaxy. When we compare it to other LAEs and green P galaxies at low redshift, we see that it's on the high end of the low redshift LAEs, but kind of on the lower end of the higher redshift galaxies, LAEs. But the main question that I was asking is whether this galaxy leaks any ionizing radiation. Who's for yes? Who's for no? Oh, okay. Well, it leaks about 15%, which is not super bad. It's not super great, but it's not 1%. So I would say good result. So if we look at the peak separation, it points it towards, okay, I said 15, it was about 18, but plus or minus, it puts it at 15. But since we didn't want to use just one tracer of ionizing radiation, because there is some controversy about the peak separation as well, because it cannot be easy, we also use the escape fraction of Lyman alpha line to measure the escape fraction of Lyman continuum. We also use the UV slope to measure the ionizing escape fraction, and then multivariate models, which were introduced by Anne Jeska. And all of them point towards escape of radiation of more than 10%. But what I want to point out is that these two are exclusive to proximate galaxies because we have the full equivalent width of the Lyman alpha line and the full peak separation. So we were very happy. Then when we look at the ionizing output, ionizing photon production efficiency of this galaxy, it's also quite high. It's nothing too, nothing too extreme. It's pretty normal. And when we construct these two numbers together, we get the full ionizing output of these galaxies, which we compare to low redshift sources and also to high redshift sources. And then we compared it to the assumed ionizing output in all the reionization models that say whether we have enough photons by galaxies to finish reionization on time. So as you can see, Lyman alpha, LAE11, I don't know if I said that's the name of the galaxy, but it is. It sits basically in the middle of all the models. The only one it kind of disagrees with is the one by Robertson from 2013, which is quite an older model. So we were very happy. But these proximate galaxies are not only good to find something about reionization, it's also good to figure something out about the quasar environment. So what I showed you before, the proximity zone with the quasar spectra, it tells you where it extends. But these double-peaked LAEs can also tell us something about the opening angle of the quasar ionization region. When we assume that it actually goes in biconal geometry. So we assume that here is the torus and it's actually going this way. And since we are looking at the quasar, we know that we are looking into the cone. But the galaxy is sitting in the ionized region, so it also has to see something similar to us. So both us and the galaxy see the ionization radiation, which gives us the upper limit on the opening angle. It could, of course, be this one, but we want lower limit, not upper limit, on the quasar. Another thing we can find out is the lifetime of this quasar, or figure out how long it's been on. And that's because the galaxy itself has some time delay on reporting when the ionizing radiation from the quasar started emerging. So we see the quasar at the time of observation, but the galaxy sees it also at the time of observation, but then it had to reionize the region around the galaxy, and then the galaxy reports it back to us. So there is some time delay. And it tells us that the quasar has been on for at least 400,000 years before the time of observation. If we compare it to the lifetimes of other quasars, either at low redshift or high redshift, we see that it's not super young, which is this group of quasars. It kind of sits in the older parts. I don't know, I would call it adult. It's not super old. It's in the middle-aged quasar. So not too bad. And the last thing that we can kind of look at is the star formation history of the galaxy and use models that talk about how the ionizing radiation from the quasars can delay star formation in galaxies around it. So by looking at the UV intensity around LAE11 and using the models by Kashikawa et al. From 2007, we found that the star formation rate could be delayed by about 50 million years in halos of mass lower than 10 to the power of 10. And when we look at the star formation history of the galaxy, we see that most of it happened in the last 5 million years. So maybe there is suppression by quasar. But the thing is that we cannot really disentangle this phenomenon from just stochastic star formation. Maybe this would have happened whether the quasar is there or not. So it would be cool to actually properly see it, but actually I can't say anything determinate. And last but not least, I want to give a small sneak peek. So if you remember the first double peak proximate LAE at the redshift 5.8 by my supervisor, she had data taken by the LBT of other galaxy candidates around this quasar, which I am now reducing. And I found these two blobs. Maybe there's another LAE with two peaks around this quasar. So this is the first one. Mine is elsewhere. I can't tell you exactly where this one is located. I have to cross-match it. But it seems good. I don't want to be super hopeful because it could be an O3 emitter at low redshift. But please stay tuned. Maybe there will be a third one. We'll see. But yeah, I'm going to leave you with my conclusions, and I'm happy to take questions. Thank you so much.
Questions?
Yes.
Emma? Yeah.
Yes, Emma.
You mentioned that you need double peaks to determine the escape fraction on the galaxies. But in the area of GWC, is that still correct? Now we have systemic redshift from the oxygen tree, so you need one peak and know what the redshift is.
That's true, but you also have to think about the fact that not all of them can have the like double peaks, even though
If you see the shift between the
that's true. That is true. It could happen. But what I also found out in this galaxy was that the O3 redshift didn't really fit with the Lyman alpha line that well. So let me go back. Yes. So when I found the redshift of this, it fell actually on this part. So that's where it was showing. It would basically mean that the blue peak is at the redshift of the galaxy, which would make it like triple peaked, but that seemed a little too extreme. So we were very cautious. And we found another paper that was comparing module A and module B, where the redshift fell on, and they found some discrepancy between the two modes. So maybe, but you're right, it could be easier if you have higher enough resolution of Lyman alpha line.
Thank you.
Yes.
I have a very minor question actually. It's about the double peak Lyman alpha profile. You showed rough and cute plot with the IgM and transmission and the suppressed blue part double peak.
Yes.
So which IgM transmission prescription do you use? I mean, given that difference choice can lead to very different influence for intrinsic group.
It really can. So the models that we were using are, where is it? It was from this paper by Charlotte Mason and from 2020. That's the ones we used. This is actually the correct one. My illustration is a little bad. This one, where I just cut it off exactly at the blue peak, but I just wanted to be illustrative.
And according to the author, Mason and Gronke, maybe it could be model based.
Yeah, it's true. Yeah.
Esther, do you want to pick up?
Sure. Hi. Let me see if I can do this. All right. Hi. So one of the things I was curious about was in this case, you've actually chosen a broad absorption line quasar, and that in itself is a very special population. And so in terms of total numbers, I'm curious if you have some comments about how that weighting and your observations there might affect your conclusion.
I'm not sure if I understand the question completely. Do you mean how the quasar affects the radiation from the galaxy itself?
No, it's more that as a class, the broad absorption line quasars are very special.
Yes.
They're often identified with local regions where you might have a higher density
Mhm.
the parent galaxy and a different enrichment history as well.
Mhm.
Okay. So I'm wondering um, uh, in if in your speculation you can comment about whether that may also change some of the kind of conclusions that you might be making.
Mhm. So we haven't considered it during the paper, but I think it's quite a good comment actually to look at later, and to actually figure out if it affects. Because the previous one, I don't think it's a broad absorption line quasar that it has been found at. But yeah, I don't know. But it's a good thing to check. Thank you.
Um, can I ask can I
Yeah.
ask another question or make another point? Um,
Uh-huh.
so another thing that may be relevant work that you might be interested in is in terms of the work that's coming out from both Subaru and from Keck in high resolution
Mhm.
spectroscopy. You in one of the references in your paper was something that uh, I and some other people had worked on, and there's a much more recent paper that we have. This is work with mostly with Tony Sangala Cowie, okay, and
Mhm.
Amy Barger and a few other people from the Lyman Alpha end. And what was done there was to once Hypersue Prime Cam became available with its much wider field of view.
Mhm.
Sorry, I swallowed the wrong way.
Oh.
One of the things that was interesting to us was what would happen if we targeted, instead of the quasar population, the high luminosity Lyman alpha population.
Mhm.
Okay. Um, and so you might be interested in terms of the multiple component Lyman alpha structures, which are seen with multiple components on both
Mhm.
red and blue side. The There's a recent paper from 2024 that we have out,
Mhm.
which shows the selection that we made with by Lyman alpha equivalent with
Mhm.
over very wide fields. I mean, one of the fields was the Hawaii Rosita field, which is about 44 contiguous degrees, multiple
Mhm.
band passes, colors, and in the narrow bands at 5.7 and 6.6. Okay. And what was done there was to choose in that, in a sample where there is an emission line threshold, okay, the detailed um, geometry of multiple Lyman alpha emitters and to make a determination of the escape fraction in those
Oh,
cases.
okay.
Okay.
Mhm.
In that case, what one's getting is that in the context of Lyman alpha emission systems, okay, um, we're basically trying to look at an environment where the fact of the suppression by the intervening Lyman alpha forest can largely be removed. If we take this with the emission line threshold, where we both begin to see the multiple components, and we go in, and now where we're using things like, well, we have used demos in the past, but now we're moving on to the my brain is going the cosmic web images, KCWI, for these studies for very high redshift and extent. Okay, the basic result that we're getting is that the escape fraction that's coming out from these systems is probably around sort of like 15% or 20%. It's basically in the context of Lyman alpha emission line systems, what you would see if you would go back to redshift 2, where the intervening medium is not such a problem. And the reason that we wanted to focus on this is this is an approach that's sort of like in between the rarer cases of quasars at high redshifts, okay, where and the really high luminosity end of the Lyman alpha emitting systems, where we can now say, what happens if we use these as the samples to both look for the distribution of the multiple components, to have both the emission line and the underlying nearby continuum colors to figure out what escape fraction is computed. And again, this is in some sense, this would be a limiting case because the big problem that you have if you use the large scale samples that people have been developing with the narrowband filters without a luminosity threshold is you basically see profiles that almost look identical, you know, because it's all determined by the absorbing gas. Okay. So the intent behind this was to both say, what can we see about both the evolution with redshift, between, let's say, the 5.7 and the 6.6 systems, and the escape fraction, and also with these multiple components, okay? And the other idea was that for both the theoretical modeling and for looking in and saying, well, we're also picking up things that are AGN that might also be um, um, hopefully, at some point, quasars as well. So, in these cases, at the threshold we're applying, maybe something like 1/7, 14% of these cases. We wanted to know what the numbers would be AGN. And the idea is also to study the differences between both the star-forming populations and the AGN fractions and their evolution in these high redshift systems. Okay, so this is sort of like been really the 2024 paper is the with a threshold of these multi-component Lyman alpha systems. You actually, I think you referenced an earlier paper from 2018 when we were just beginning to find and do complete statistics on these. Okay. And you might be interested in just trying to put those numbers in and those thresholds and what we're seeing in terms of the relative evolution rate, because we can see that in the numbers between 5.7 and 6.5 of things going up as you apply a slightly different threshold. You can probably use that in connection with your own modeling.
It's possible. I can't tell it to you right now off the top of my
No,
head.
but I'm just I can put up in the chat or something.
Yeah, I would love to, if you could.
Esther, are you in Manoa or in Kilo?
I'm in Manoa. I mean the main IFA facility and where we teach, and where we teach classes.
Otherwise, you could have just come over.
Yeah.
No, well,
have a chat.
But
the last time I was over there was, I guess it was in June when we were trying to use the prime focus spectrograph on this project, and we had terrible weather. I mean, well, let me say that one of the measures that they used for how bad the weather was the effective exposure in terms of what should be assumed if there's no extinction like in these systems, and it's 500. We actually had one observing run where the measured effective exposure that we're getting through the emission line system was 10 on that time.
Yeah, that's pretty bad.
So that really was pretty bad, and we're going to try again. But the thing about being able to use some of the instruments like KCWI and so on, one of the things that we're trying to use with the um, larger collecting area of the telescopes is to get get the resolution down so that you can see both more of the separation when you're doing things like the night sky subtraction, for example. Um, you're less, you can be more confident about finding residuals and components that are close to the emission line systems. That's one of the problems that you were talking about using it in the data.
There seems to be a long discussion.
Yeah. I mean,
you have you see on the screen there is Klaudia email.
Yes, I'd be happy to chat.
So you probably can chat about that.
okay. Let me see. Maybe I can put up, hold on, let me find the chat. Let me find okay, so this is here. I think I can put down.
Meanwhile, while you're sharing, is there?
Okay, so this is the actual, this is the paper. But if you want to look at other papers from this work, actually, the NASA grant that we were working from actually requires us to put things in a publicly available archive. Let's see if I hold on. Sorry.
While you're looking to that, is there any last question before we close the talk?
Okay, I'm sorry.
Brian?
Hold on. Let me. It's this cut and paste sort of thing. Let me.
I have a, so if you go, I don't know if it's one slide back or one slide forward that shows the image of the quasar with the image of your galaxy. So this one is great. And the proximity zone where you're getting basically ionization from the quasar that kind of protects it, right? Do you expect, it's a fairly dense field. Do you expect to find other galaxies that are also in this proximal zone?
So there is 12 LAs around this quasar. And I think there are also 3 radio galaxies, or some that have been found with a C2 line in ALMA. So it's probably not a radio galaxy. And I'm sure there are also Lyman break galaxies around this quasar field. But all the LAs that have been imagined, they're actually not all here. Feiga Wang still has the others, so I haven't seen it. I've just been sent these 12 ones to look at. But it is possible that maybe there are others. I just don't know about them.
Thank you.
Oh,
Esther, do you want
so
to share your? Yeah. And then we close.
Okay.
Or you can send it on email.
Yes.
Well, I just, in the chat, the second thing that I put up, National Science Foundation requires all grant holders to put publications that reflect the grant into this publicly accessible archive. So that's, if you put up the grant number, which was in any one of those papers, in that format, you'll see a whole list of papers that anybody can download. They also have to be in accessible PDF format. So if you're low vision or blind, you can read this too. But you can find other papers there.
Thank you so much.
Okay.
Thank you. So we reached the top of the hour. So we want to just thank Klaudia again.
Thank you.
Okay.
We'll be on this time going for 5 more weeks. So if any questions come in, please write to her or come to Gemini,
Yes,
which is a good place.
it's super nice.